Welcome, this is the presentation for our WACV 2024 paper titled, Effective Restoration of Source Knowledge and Continual Test Time Adaptation. In real-world applications, domain shift is a prevalent challenge arising from variations in data distributions over time or across different environments. Factors such as changes in data sources, lighting conditions, or demographics can contribute to domain shifts. Such domain gap can deteriorate the performance of deep learning models by a significant margin. Hence, addressing these shifts is crucial for the robust performance of machine learning models in diverse and evolving scenarios. Test time adaptation or TTA is a dynamic process wherein a pre-trained model adapts itself to streaming data batches from the target distribution in real time. Continual test time adaptation takes this a step further, dealing with a target distribution which undergoes continuous changes. What adds to the complexity is that the model, during adaptation, only has access to a small batch of data at any given moment. Once the adaptation is completed for that specific batch, the data is no longer accessible. Additionally, the source dataset is unavailable. The combination of these factors poses a formidable challenge for test time adaptation. The model must refine itself with each incoming batch of data, such that its performance is enhanced on subsequent batches. There are two major challenges that TTA methods face when dealing with continually changing target distribution. The first challenge is recognized as catastrophic forgetting, wherein previously acquired source knowledge is at risk of being lost. As TTA methods adapt to new domains over an extended period, there is a potential drift in model parameters, leading to the forgetting of vital source knowledge. Moreover, the gradual misalignment of pseudo-labels due to domain changes also contributes to the degradation in performance. To illustrate this point, consider the figure depicting a well-known TTA method, TENT. With each introduction of a new domain, TENT experiences drastic performance degradation, primarily attributable to these two factors. To overcome these challenges, one intuitive approach can be to reset the model parameters to the original source pre-trained weights whenever there's a change in the domain. By restoring the knowledge from the source, the negative consequences arising from the gradual deterioration of model parameters caused by ongoing domain shifts can be corrected. In fact, some prior studies have demonstrated the benefits of such model resets. However, it is important to note that these studies rely on an oracle with ground truth domain knowledge to determine when to reset the model upon encountering a domain change. This reliance on ground truth domain knowledge makes the approach impractical for real-world scenarios. In our work, we pose the question, can we detect domain changes in continual TTA in an unsupervised manner without any ground truth domain knowledge? Our proposed method is designed to address this challenge. More precisely, we introduce a domain change detection module that can identify domain shifts in an unsupervised manner and subsequently reset the model parameters. This innovative approach allows our method to operate seamlessly with any existing TTA methods, enhancing their performance in scenarios involving continually changing target distributions. The batch normalization layers in deep learning models have the capability to encode domain information. To demonstrate this, we utilize a ResNet-18 model that has been pre-trained on ImageNet. We extract the batch normalization means for each data batch from various domains within the OfficeNet dataset. We present here a TSNE visualization of the extracted means. The visualization clearly illustrates that the means are organized into clusters corresponding to different domains. This observation suggests that batch normalization statistics can serve as valuable indicators for detecting domain changes. In our approach, we estimate the global batch normalization statistics for a given domain using a running average. We introduce an adaptive momentum into the running average calculation, where the momentum value is determined by the callback labeler, KL, divergence between the running statistics and the current statistics derived from the incoming batch. Upon the introduction of a new domain, the initial KL value is typically high due to the mismatch between the running statistics and the current statistics of the new domain. However, as the model encounters more data batches from the new domain, the running statistics gradually align with the global batch normalization statistics of that specific domain. This alignment results in a progressive reduction of the KL value and, consequently, the adaptive momentum. We also monitor the largest domain gap, represented by the highest KL value, and normalize the adaptive momentum using this value. This normalization ensures that the adaptive momentum remains within the range of 0 to 1. Whenever a domain change occurs, the data batch from the new domain causes the adaptive momentum to spike again. By detecting these peaks using any online peak detection algorithm, we can effectively identify domain changes in an unsupervised manner. In our paper, we have conducted a comprehensive set of experiments involving a diverse array of datasets. Each dataset encompasses a wide range of domains to ensure a thorough evaluation of our approach. Our experiments cover tasks related to both classification and segmentation. Here are some key findings from our experiments. In essence, our method effectively extends existing TTA methods to dynamic scenarios, substantially enhancing their performance. When integrated with existing TTA methods, our approach demonstrates improved performance compared to state-of-the-art continual TTA methods. Additionally, our method outperforms existing approaches in retaining source knowledge. And here are some additional plots depicting the adaptive momentum values with respect to incoming data batches from different domains. Notably, our approach consistently exhibits a peak in the occurrence of a domain shift. In this figure, instances where our method successfully detects a domain change and subsequently resets model parameters are highlighted with vertical bars. The clear alignment of these bars with actual domain changes demonstrates the high success rate of our method in accurately identifying dynamic shifts in the data distribution. This visual representation underscores the efficacy and reliability of our approach, showcasing its effectiveness in real-world scenarios. Thank you.